Hey everyone, my name's Nathan Dahl. I am a weather research scientist, and I gotta tell you, I think all weather is interesting, but the most interesting weather for me is the kind that spins. So that's the kind that I'm going to be talking about today. Now, before we get started, I want to make sure you have the following things. First off, a ball of dough or clay on a stick, or if you don't have that, a globe, a piece of fruit, a ball, something that you can spin in your hand, a cardboard tube, a sink that's about half full of water that's been sitting for a while, something to sprinkle on the water that will float and that won't clog up your drain, a regular pencil with an eraser, some colored pencils, and the 4 handouts that should be attached to this lesson. Now, if you've got all that squared away, let's get started. Now, when it comes to weather that spins, there are a lot of different kinds. Here's a little dust devil that you might see spinning across a parking lot or a field sometime. And here's a view from the middle of a gigantic storm, hundreds of miles wide, spinning over the ocean. You might be wondering, with all these different kinds of spinning weather, where does all the spin come from? Well, it all starts with the fact that we live on this spinning ball called Earth. Okay, so this isn't actually Earth. It's a glob of Play-Doh with a chopstick shoved through the middle of it. But I'm going to use it as a visual aid to keep track of how the Earth moves. See, we can imagine that the Earth is a ball with a stick through the middle, called the axis, with the North Pole here and the South Pole here, and the Earth spins like this, around that axis, from left to right, or we might say from west to east. Now, go ahead and grab your visual aid as well and start spinning it like this. Now let's imagine we're in a spaceship, and we're looking down on the Earth. Now from here, from near the middle, the equator, it looks like the Earth is just spinning from left to right. But let's pretend now that we take our spaceship and fly it up here to the North Pole and look down on the Earth from there. So start spinning your visual aid, whatever it might be, and look down on it from above. It might look like this. Now you see, instead of spinning from left to right, now it looks like the Earth is spinning this way, counterclockwise. So let's go back to the equator. Keep spinning. That's how I think spaceships sound. Don't worry about it. And now let's pretend we fly down to the South Pole and look at the Earth spin from there. See, looking at it from the South Pole, it looks like the Earth's spinning in the opposite direction from what we saw before. Now it looks like it's spinning clockwise. So, the way the Earth's spin looks changes depending on where we are. And understanding that change is a big deal for understanding how the Earth's weather works. Now you might be asking, what does the Earth's spin have to do with the weather? Well, if you want to take out your handout number 1, this is how the Earth looks from the North Pole. And we are going to see right now how the Earth's spin changes the way things move. What we're going to do here is we're going to go on a little bit of a trip. You see this point A and point B? Well, point A here is the North Pole, and point B is Oklahoma. Because who doesn't want to go to Oklahoma? I know it's a little weird to see the U.S. upside down like that, but see, there's the U.S., there's Oklahoma. Good stuff. Now, first, we're going to act like the Earth isn't spinning. So we're going to just start at A and draw a straight line to B, like this. See? No problem. Now we're going to do the same thing, but now the Earth is going to spin. Remember, it spins counterclockwise in the northern hemisphere, so draw a line straight up the page, but as you do, turn the paper like this. Ready? 1, 2, 3. Oh, look what happened there. See, it didn't go straight. It bent off to the right because of the way the Earth spins. Now, we're going to try that again. Get handout 2. Now this is how it looks from the South Pole. This is the southern hemisphere. This time, for our trip, we're going to go from the South Pole to Sydney, Australia, where my grandmother's from. Okay, so same thing. First, pretend that the Earth isn't spinning, and just straight from A to B, like that. Now, we're going to add in the spin of the Earth. See, this time, the Earth spins clockwise, so turn the paper this way while you're drawing. Ready? 1, 2, 3. So this time, instead of going straight where we meant to do, we curved off to the left because of the way the Earth spins. So you can see that where you would just go straight where you're pointed if the Earth weren't spinning, like this. Instead, with the Earth spinning, counterclockwise in the northern hemisphere, you wind up off to the right from where you meant to be. Now, in the southern hemisphere, where things spin clockwise, you wind up to the left of where you wanted to be. Now, this shift to the right or to the left is called the Coriolis force. And it's named after this guy, Gaspard Gustave de Coriolis. He's a French scientist who wrote about it 200 years ago, so we've known about it for quite a while. So, you might be wondering, hang on, if I'm playing catch in the backyard, do I have to worry about the Coriolis force moving the ball around? The good news is, no, you don't. See, the Coriolis force depends on how quickly something is spinning around, how long it takes for it to complete one spin. And the Earth takes a whole day, 24 hours, 86,400 seconds to spin around one time. Meanwhile, when you throw a ball, that only takes about 1 second. Things that only take a few seconds, a ball flying through the air, draining a sink, flushing a toilet, those things don't care about the Coriolis force at all. On the other hand, weather systems, storms that take hours or days or even weeks, for those, the Coriolis force can matter a good deal. So to see what the Coriolis force does to the weather, let's review a bit about why air moves in the first place. You might have seen a weather map like this before. The red and blue lines divide warm air to the south and east from cold air to the north and west. And that brown line is a dry line, dividing dry air to the west from more moist, humid air to the east. Now, we're not really going to talk about those lines a lot right now. If you want to learn more about them, Pat Hyland gave a good lesson about this a few months ago. For right now, the most important things on this map are the big blue letter H over Michigan, Indiana, and Ohio up there, and this big red letter L over Texas, Kansas, and Oklahoma. Now, the big H stands for high pressure, and the big L stands for low pressure. So let's talk a bit about what that means. Right now, this is you, and you are surrounded by air, and it's pressing in on you from all sides, and we call that air pressure, or just pressure. Now, air pressure is okay. It's not a problem for you. Your body's used to it. See how happy you are? In a way, you and I live in an ocean of air, which we call the atmosphere. So imagine that black line on top is the top of this ocean of air. The amount of air pressure where you are depends on how much air is piled up on top of you. So, if the top of the ocean of air is flat like this, then the pressure is the same everywhere. All these trees feel the same amount of air pressure. But actually, the atmosphere has waves, the same as an ocean or a lake or water in a swimming pool. So say it looks like this, where the top is higher at the crest of these waves here, underneath that you have high pressure. And where it's lower, right here, you have low pressure underneath. So we talk about high pressure and low pressure. What does that have to do with air moving? And why are we looking at a pan full of milk right now? Well, we can't see air, but we can see milk. And milk and air kind of act in a similar way for stuff like this. So let's pile up a lot of milk on one side of this pan and see what happens. Okay, so we've got a lot of milk on the left side of the pan. And we could say that there's high pressure on the left. And on the right side, there's not as much milk, so we could say that there's low pressure on the right side of this pan. So what happens next? You want to take a guess? Well, I'll show you. It sloshes back from left to right. Slosh. So there are two things to take away from this. First, crying over spilled milk. Don't do it. But more importantly, whether you're talking about milk or air, it wants to be spread out evenly. It doesn't want to be piled up in spots like this. So what happens is if you have higher pressure here and lower pressure here, the air will be forced away from the high pressure and toward the low pressure. Remember how the milk sloshed away from the high pressure toward the low pressure? Same thing with air. And we call the thing that pushes air this way the pressure gradient force. Now that's a lot of words. Let me just explain what they mean. The word gradient just means change. There's a change in pressure from high to low here, or from high to low here. In between these, there's a change in pressure, or a pressure gradient. And this pressure change forces the air toward lower pressure. Pressure gradient force. So let's go ahead and talk a bit more about weather. You know, that stuff that I said was so interesting. Go ahead and find handout 3, which looks like this. Here's the US, and you have the high pressure here at the big H, and you have the low pressure here at the big L. Go ahead and color those in if you want. I already did because I'm a cheater. Now, take your regular pencil and just very lightly draw some arrows going toward low pressure. Kind of like this. Now that's the direction the wind would move. That's the direction that the wind would blow if the Earth weren't spinning. It would just go straight towards low pressure. But don't forget, the Earth is spinning. Remember this handout before where we saw that when we spin the Earth, it makes things go off to the right in the northern hemisphere, where the US is? So now, what you're going to want to do is take a pencil, your favorite color, mine's green, and draw arrows to the right of the arrows you drew before, like this. So, that is the direction that the wind actually blows. It goes off to the right because of the Coriolis force. So we don't need those arrows we drew before. Those are wrong, so go ahead and erase them. So what do you see with these green arrows? Instead of going straight towards low pressure, they're kind of swirling around it. You see that? They're swirling around it and into it. So we can make this a little more obvious by drawing what's called a trajectory. So take a black colored pencil or another color if you like, and we're going to make a trajectory starting here in the Gulf of Mexico. Now what a trajectory means is we just kind of follow the arrows. So first we see, the closest arrow is this one, is kind of going that way. So we start off heading that way, and then we see this arrow that kind of turns that way, and so we do the same. And then this arrow kind of turns that way, and so we kind of do the same. And we keep on going, just trying to follow the arrows as best we can. And we wind up here. So that was a lot of steps. Let's go back and review that real quick. We started off with the high and the low pressure, and we drew these little arrows going straight towards low pressure. That's what the wind would do if the Earth weren't spinning. But the Earth is spinning, so because of the Coriolis force, the real wind is actually going off to the right a bit, like that. So we drew some more arrows. Then we got rid of the wrong arrows that we had before, and this is what the wind actually does. It doesn't go straight towards low pressure, it kind of swirls around it. And then we started in the Gulf of Mexico and we made a trajectory. We're kind of pretending like we're a feather or a balloon, something that's just riding with the wind wherever it goes. And this is the path we would take, is something like this. Kind of swirling around and spiraling into the low pressure. This low pressure center, with the wind swirling around it, is called a cyclone. And cyclones are a really big deal when it comes to intense weather. And for example, take a look at this thing. This was a really nasty cyclone that hit the Gulf Coast 15 years ago. It was a long time ago, but it was bad enough that you might have heard of it anyway. It was called Hurricane Katrina. This is what that storm looked like from outer space. Now you can see how big it is. That right there is the entire state of Florida. And Hurricane Katrina was almost that big, hundreds of miles across. But the storm didn't start out that way. It started out just looking like a bunch of ordinary thunderstorms over there in the Atlantic Ocean. So let's zoom over there and see what it looked like when Hurricane Katrina first started up. So at first, there's not a lot going on. You see these blobs here, these white blobs, those are just ordinary thunderstorms. That's how cumulonimbus clouds, thunder clouds, look from space. And at first, we just have these regular thunderstorms bubbling up and then dying off and then bubbling up and then dying off, and then watch what happens. All of a sudden, a whole bunch of them bubble up and kind of glob together right here. And as that glob moves off to the west, it starts to spin. What's happened here is that a low pressure center has developed, and the winds are swirling around it. It's become a cyclone, a tropical cyclone. This cyclone moves over South Florida. It's still pretty small, but watch what happens when it gets over the warm waters in the Gulf of Mexico. It gets bigger and bigger, and it spins faster and faster, and now it's turned into a monster. It has this open area in the middle called the eye, and in this big ring of clouds around the eye, the fastest winds are spinning at over 170 miles per hour. So just to give you an idea, if you were standing outside and a 60-mile-an-hour wind hit you, it might be enough to knock you over or to tear branches off a tree. Well, try to imagine what a 170-mile-an-hour wind would do. Now you might be wondering, why does this storm have an opening in the middle? Why does it have an eye? So to illustrate, I'm going to make a fool out of myself now and pretend to be a hurricane. Whee! Okay, that's enough. I feel silly and I don't want to throw up, so I'm going to stop. But here's the idea. When I'm spinning around like this, out here, my arms and my hands are moving really, really fast. But here in the middle, like my head, isn't really moving very much at all. And it's the same in a hurricane. You still have low pressure near the ground, but up above it there's not a lot going on. So the air up there just kind of sinks toward the low pressure near the ground, and the sky's clear, and you've got this calm, clear area, this little spot, surrounded by storm on all sides. That's the eye. Now, as long as this storm is out over water, it has a lot of warm, moist ocean air feeding it, and it just keeps getting stronger. Now watch what happens when it goes over land. It slows down and it gets all raggedy, and eventually it dies out. Now tropical cyclones like this need warm ocean water to survive. Once they get over land, they start to run out of fuel. They can still dump a lot of rain and they might put out some gusty winds over here, but nothing like this. Tropical cyclones pop up all over the world, where the oceans are warm. But they're called different things in different parts of the world. Over the Atlantic Ocean and the Eastern Pacific Ocean, in this orange area here, they're called hurricanes. Now in that purple area over on the right, by China and Japan, they're called typhoons. And in that yellow area there, from Australia to the east coast of Africa, they're just called cyclones. And we also started giving them people's names a while ago, like Katrina, or Sandy, or Dorian, a big hurricane that hit the Bahamas last year. But all these different names and terms are all talking about the same kind of storm. Now, let's compare Hurricane Katrina, which hit here in the northern hemisphere on the Gulf Coast of the United States, with a tropical cyclone, Cyclone Ilsa, that hit here in the southern hemisphere near Australia. Now here we have views from space of Hurricane Katrina over here on the left and Cyclone Ilsa over here on the right. Now what do you notice about the direction the clouds swirl around them? For Katrina, the clouds swirl this way, counterclockwise. For Ilsa, though, you can see that the clouds swirl the other way. They swirl clockwise. That's because, remember that in the southern hemisphere, where Ilsa happened, the Coriolis force bends things to the left, not to the right. So cyclones in the south spin in the opposite direction from cyclones in the north. Ilsa also wasn't as strong as Katrina was. Other than that, though, they're the same kind of storm, a tropical cyclone. Now remember that tropical cyclones get stronger over warm water, but then weaken and die out after they go over land. So, does that mean that cyclones that happen over land don't cause really bad weather? No, they can. Let's look at something that happens every year in the southern United States. So we're going back to this map we saw earlier, you remember? With the big red L showing where the cyclone is, and that brown line showing where the dry line is. Now remember, when you have a cyclone in the US, near the ground the winds swirl into it counterclockwise, like that. So here, we've got winds like this bringing warm, moist air up from the Gulf of Mexico. Now that warm, moist air is fuel for thunderstorms. Now farther up, miles above the ground, way, way up, you'll often have strong winds blowing out of the west, called the jet stream. So you see the area in this box where it looks like everything is going on? Let's take a closer look inside that box. Well, this is what it looks like from ground level. So go ahead and grab handout number 4, the one that looks like this, and pause the video and color it in if you like. I cheated and colored mine in early, again. So now, after you've done that, grab your cardboard tube, and we're going to see how all of these ingredients come together. So imagine, instead of being made of cardboard, this tube is a tube of warm, moist air coming in from the Gulf of Mexico. So point it along this arrow right here. Now, we have the jet stream going over the top, high above the ground like this, and what it does is it takes this tube of air and kind of shears it over like that. So it starts to tumble like this, kind of like a football if you threw it. So go ahead and draw in some arrows showing how it tumbles, kind of like this. Okay? So, what happens when this tumbling tube of air meets a thunderstorm? Now, the reason I drew this big up arrow to show a thunderstorm is that thunderstorms have air rising really, really fast in them. It's called an updraft. And when this tumbling tube of warm, moist air meets that updraft, it gets tilted like this until it's pointed up and down. And instead of tumbling like this, the way it was before, now it's spinning left to right, like a cyclone in the northern hemisphere, remember? And the whole thunderstorm starts to spin like this. Go ahead and draw some arrows, like this, showing the whole thunderstorm spinning. Now what we call this whole thunderstorm spinning is a supercell. And supercells can get really, really strong. Let's go ahead and try to imagine what this thunderstorm might look like. I mean, you got a big old cumulonimbus cloud with the top of it getting dragged over by the jet stream like that. And it's spinning, so we got some little contours like that. And way out here, it's dropping a lot of rain, or maybe even some hail. And of course, it's a thunderstorm, so it's dropping a whole lot of lightning. And yellow doesn't show up really well on this. But that's what I've got. Hopefully your drawing's a little bit better. But let's actually look at a supercell and see how close we got. So I'll tell you, I looked around for videos of entire supercells that we could compare the drawings to, and this is the best one I could find, and it's not a real supercell. It's actually a supercell that was made in a computer model. That's what it looks like. It's a giant, single rotating updraft that reaches about 10 miles into the sky, where it spreads out like this. So let's take a look at how this thing moves. You can see this kind of band of warm, moist air, this cloud that's feeding into it from the side. Well, this air that's being sucked up into the supercell, when it's out away from the storm, you can't see it real well, but it's kind of tumbling like that. But when it gets sucked into the storm and rises up a little bit, now the whole thing is spinning like that, like a top. That is a supercell. And I'm not going to lie, it's pretty awesome to look at. But they can also be dangerous if you get caught outside in them. Lightning from thunderstorms kills about 100 people in the US every year. Heavy rain from thunderstorms can cause these big flash floods that'll sweep you away without warning if you're outside. And supercell thunderstorms in particular can drop some giant hail the size of baseballs, maybe even grapefruit. Think about a ball of ice the size of a grapefruit falling from 30,000 feet in the air and hitting you in the head. You don't want to be outside for that. And then there's the thing that supercells are perhaps best known for, tornadoes. Now, a tornado is a strong rotating column of air extending from the bottom of a thunderstorm cloud to the ground. You can see that in this video here. This is video of a violent tornado that hit Moore, Oklahoma back in 2013. Not all tornadoes are really violent. There's a wide range. There are weak tornadoes, there are strong tornadoes, there are violent tornadoes. The problem is that it's really, really tough to try to measure the wind speeds in a tornado. They're small, they move around a lot, they don't happen really often, and most of them are strong enough that if you try to put an instrument inside them to measure the winds, like an anemometer, it'll just break it right up. So instead of going off of wind speed measurements, we rate tornadoes based on the damage that they cause, using what's called the Enhanced Fujita scale, or the EF scale. The weakest tornadoes are rated EF0. We're talking about winds about 75 miles an hour, which is strong. You wouldn't want to be outside in one. But it doesn't really cause much damage. Can you find the damage the EF0 tornado did to this house? Well, if you're having trouble, let me help you out. Right there, you see those shingles that have been peeled back? Also, a window has been broken, and the siding of the house has been roughed up in spots. That's the sort of damage you would expect to get from an EF0 tornado. Now, stronger tornadoes have higher ratings. This is damage from an EF1 tornado with winds around 100 miles an hour. Can you see it? Well, part of the roof has been removed, and the garage door has been bashed in. Here's damage from an EF2 tornado with winds around 125 miles an hour, and you can see most of the roof has been removed now, and if you look through that window, you can see that one of the back walls has been knocked down. This is damage from an EF3 tornado with winds around 150 miles an hour. Most of the outside walls have been completely knocked down, and the roof has been totally taken away. If you look closely, you can see a stove and a microwave. We're looking into the kitchen right now. This is damage from an EF4 tornado with winds around 175 miles an hour. And here, the house has been completely knocked down, mostly made into a pile of rubble. And finally, this is the highest rating on the Enhanced Fujita scale, EF5, with wind speeds of 200 miles an hour or more, and the house is just about completely gone. Now, before you get really scared, you should know that very, very few tornadoes are EF4 or EF5. Most tornadoes, if you're in the middle of a sturdy building, you'll be just fine. But you do not want to be outside when a tornado is around. You need to get to the lowest floor of a sturdy building, preferably underground if you can, and stay there until the tornado passes or dies out. Going back to the video of the Moore tornado, you might notice something. Remember that the thunderstorm above this tornado is a supercell, and the supercell spins around. You can kind of see it spinning in these bits of cloud right here. But it's not spinning very fast, is it? Now look at the tornado near the ground. You can see that it's spinning a lot faster. And that's what makes tornadoes so destructive. So you remember that silly thing I did a little while ago where I held my arms way out and I spun around pretending to be a hurricane? Well, I'm going to do the same thing again, and this time I'm going to pretend to be a tornado. And you can do it along with me if you like. Just make sure that you have plenty of room as you're spinning around so you don't hit anything. Probably best to do it on carpet or something soft so you don't hurt yourself if you fall over. And if you get motion sick, you might want to sit this one out. But what I'm going to do is I'm going to hold my arms out like this, and I'm going to spin around as fast as I can. Then I'm going to say 3, 2, 1, and I'm going to pull my arms in close like this. And I'm going to keep spinning as fast as I can. And we're going to see how things change. And if you do it along with me, pay attention to how fast you're spinning and how it feels, how hard you have to work to keep spinning that fast with your arms out versus with your arms in. So ready, and go. 3, 2, 1. Okay. Let's go to instant replay and see what changed. Now, it can be tough to keep track of something that's spinning around, especially when there's arms flying around all over the place. So what I want you to do when I play this video again is to count along with me out loud every time you see my head turn around so that my face is toward the camera. And pay attention to how fast you count. Ready? Go. 1, 2, 3, 4, now arms in, 5, 6, 7, 8. Do you see that? It got faster. And you might have noticed the same thing if you did it along with me. How when your arms were out, you were spinning and having to work for it, and when you pulled your arms in, it got easier to spin, and you spun faster. So there were a few different things going on there. But one of the things that was going on is something called conservation of angular momentum. Now that's a mouthful, so let's break it down. When something's moving with a lot of power, with a lot of oomph, we say that it has momentum, a lot of momentum. For example, Let's say this is an OU football player. Big, strong, fast. And on the other hand, let's say this is me. Not so big, not so strong, not so fast. Now, if we run and smack straight into each other, because I'm not very bright, who do you think's going to win? Go OU. See, because this big, strong, fast football player has a lot of momentum. And I, being not so big, not so strong, and not so fast, do not. Now, things that are spinning around also have momentum, and we call that angular momentum. Like when I was back there spinning around with my arms and my hands out like this, I had angular momentum. But it was kind of spread out. A lot of it was in my arms and my hands. And when I brought my arms and my hands in, I brought that angular momentum in with them. So now all my angular momentum was in a smaller place and I was able to spin faster. That's conservation of angular momentum. So here's why that matters for tornadoes. This is a drawing of a supercell, and a supercell spins. The wind underneath it swirls like that. Not very fast, but it's very wide. It's something like 10 miles across. So there's a lot of angular momentum there. And if you take that angular momentum and pull it into a small space, say less than a mile wide, the wind can spin very fast, and you get something like this. Now, most tornadoes come from supercells, and the reason for that is really simple. Supercells spin. Ordinary thunderstorms don't really spin, so they don't have a lot of angular momentum that can be tightened up and turned into a tornado. And to see the difference that that makes, let's try an experiment with that sink full of water that's been sitting there all this time. Now, we've been letting this sink full of water sit for a long time because when you first fill up the sink, the water's still moving around a lot after you turn off the faucet. And we want it to calm down, and so we've let it just sit there and all the little random motion has died away. Now to make sure of that, go ahead and get whatever you had to sprinkle on the water, or your little what's-it, and go ahead and sprinkle some. And you can see there's not a whole lot going on. It's pretty calm. Well, this is kind of like the air underneath an ordinary thunderstorm. You have to use a little bit of imagination. What we're going to do is we're going to pull the plug out of the drain and let the water go down the drain. And that'll be kind of like the air going up into an ordinary thunderstorm. So it's kind of like a thunderstorm upside down. You follow? Okay, so what you're going to do is you're going to put your hand in the water very carefully, disturb the water as little as possible, and at the count of 3, we're going to pull the drain straight up. Ready? 1, 2, 3. Now it's sloshing around a little bit, and yeah, there's a little bit of swirl going on in there, but really not all that much. Pretty standard stuff. So now what we're going to do is we're going to fill the sink back up. And that's going to take a little while, so I'll see you in a second. Okay, so we've got our sink back full, well, half or maybe a third full of water. And this time we're going to do something a little different before we let the water out. We're going to take your hand, just like this, and give it one swirl like that. Now it's still sloshing around a little bit. So let it calm down just a little bit. Go ahead and sprinkle some more of your what's-it on there to help you see how the water's moving. Now you can see now it's spinning. Now there's angular momentum in the water out here on the edges of the sink. And this time when we pull up the plug, all that angular momentum is going to be pulled toward the drain as the water goes out. So we're going to see what kind of a difference that makes. Same thing as before. Put your hand in carefully as possible. And ready. Pull it out. That wasn't the cleanest, but you can still see. Look at that. Look at that big whirlpool. Very, very different. So remember, the water in that first sink was kind of like an ordinary thunderstorm. Not a lot of spin to begin with, so we didn't get a really big whirlpool out of it. That second sync was kind of like a supercell where we added some swirl to it, not very much, but it still gave us a really, really big whirlpool. So if you think about it, a whirlpool is kind of like a tornado upside down. I thought that was pretty cool when I was a kid. So in this lesson, we went from a spinning Earth thousands of miles wide, to spinning tropical cyclones hundreds of miles wide, to spinning supercell thunderstorms about 10 miles wide, to spinning tornadoes less than 1 mile wide. Now, we only covered a few of the basics today. There is so much going on with these storms. At SIMS and at the Storm Prediction Center, we still have a really, really tough time trying to forecast weather like this. There is a lot left to learn. Sadly, that's all the time we have for today, so I hope you all had fun, and bye for now.